Hey everyone. In this video, we're going to be learning how to draw the structure of organic compounds. Now, the structure is not the only piece of information we can use to talk about a particular molecule. There are many different representations of a molecule. You can refer to molecules by their specific name, which we'll learn about in another video, by their molecular formula, a ball and stick model, an expanded structure, a condensed structure, or a skeleton structure. And so we'll look at all of these different methods of drawing in this video. So first, let's talk about molecular formulas. So a formula shows the total number of each type of atom in a given molecule. We always write carbon first, then hydrogen, then everything else. Formulas don't give you any specific information about the structure. They only tell you what atoms are in that molecule. So let's take a look at this molecule here. If we're looking at the carbons, we'd see that there's 1 carbon, 2 carbons, 3 carbons, 4 carbons. So that's where we get the C4 from. And then if we're looking at hydrogens, you see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. So that's where you get the 9 from. And then you also see that there's an oxygen right here and a chlorine. And so that's where the oxygen and the chlorine come in. So carbon first, then hydrogen, then everything else. Let's do a practice. So here's the molecular structure of caffeine. Can we come up with the molecular formula for caffeine? So we always want to start with carbon. So how many carbons can you count? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So C8. And then you want to do hydrogen next. So how many hydrogens do we see? 1, 2, 3. There's another one there, there. Here's 1, 7, 8, 9, 10. So I see 10 hydrogens. Well, what else do we see? I see some oxygens. And how many? Oh, I don't like that color. Let's see. Green? Let's try green. How many oxygens do we see? There's 1 there, 1 there. I only see 2. So O2. And another color. Let's do purple. Oh, didn't take. There we go. And let's do nitrogen last. Let's see, 1 nitrogen, 2 nitrogens, 3 nitrogens, 4 nitrogens. So that would be our molecular formula. It just tells us the total number of each type of atom. Doesn't tell us anything about the specific shape. Well, let's make sure we counted those correctly. C8, H10, O2, N4. Sounds good. All right. Now let's talk about hetero atoms. So what does the word hetero mean? Hetero means different, right? And so a heteroatom is any atom that's not carbon or hydrogen. So typically heteroatoms are nitrogen, oxygen, fluorine, chlorine, bromine, or iodine, maybe sulfur or phosphorus, anything that's not carbon and hydrogen. Now, when atoms form molecules, they always want to have a full valence shell of electrons. And so for everybody other than hydrogen, that's 8 electrons. Remember that from drawing Lewis structures back in chapter 6, I believe it was. So everybody wants 8 electrons. And so the number of bonds plus the number of lone pairs is always going to be equal to 4. Now, if we look at some bonding patterns, here are the bonding patterns of all the common elements we're going to see. So hydrogen, because it's in the first shell, it only needs 2 electrons, and so it only forms 1 bond. Carbon always forms 4 bonds. Nitrogen forms 3 bonds and has 1 lone pair. Oxygen forms 2 bonds and has 2 lone pairs. And halogens always have one bond and three lone pairs. And in case you forgot, halogens are fluorine, chlorine, bromine, and iodine. So those are referred to as the halogens. And so they're abbreviated here as X for any one of these four. So definitely remember these bonding patterns. This is going to be key for the rest of the semester. So make sure you have this pattern memorized. So the next thing we're going to talk about are expanded structures. So in an expanded structure, you show every bond and every atom. So this is our standard Lewis structure like we learned about in chapter 6. So if we have the formula C4H10, we have to show all 4 carbon atoms, all 10 hydrogen atoms, and all of the bonds connecting them together. Let's do a quick study check. Draw the expanded structure of ethane, C2H6. Well, if we have 2 carbons, they got to be connected to each other. Now, how many bonds do carbon form? Well, we know carbons always form 4 bonds. So that means this carbon needs another 3, and this carbon needs another 3. And we have 6 hydrogens, and it looks like they're going to fit perfectly. Hydrogen, 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 and hydrogen. And so that is our C2H6. And everybody's happy. Looks like we drew it correct. So once again, this is called the expanded structure because we're expanding and looking at every single atom and every single bond. Now, this is a little tedious to draw, and so we have a faster method known as a condensed structure. Now, in a condensed structure, we look at each carbon atom and the hydrogen atoms connected to it as a group. And we use a subscript to tell us how many hydrogen atoms are within that group. So for instance, this right here is our first carbon atom, and it's connected to 3 hydrogens. And so that would be simplified or condensed as CH3. So we took the expanded and we condensed it into a CH3. And what's that CH3 connected to? Well, it looks to me like it's connected to a CH2, 2 hydrogens on this carbon. So that's our CH2 condensed. And then the next one looks like we have another CH2. And then the last one is a CH3 again. And so the condensed structure here would be CH3 connected to a CH2, connected to CH2, connected to CH3. This is a lot quicker to write than drawing the full expanded structure. So once again, condensed, you don't show all of the bonds to hydrogen, you just condense them into groups of CHs. Let's do practice. We're looking at this molecule here. We would condense it as CH3, CH2, CH2, and CH3. We don't necessarily have to draw the bond lines between the CH3 and the CH2. So you could express this as CH3, CH2, CH2, CH3, where you're showing the bonds between each one. But you don't have to show those. You could just condense it and write the groups right next to each other. It implies the same thing. This is just further condensed. And typically, we also don't show lone pairs if there happen to be any. So let's look at another example here. If we had that CH3, CH2, CH2, CH3, notice that there's 2 CH2 groups right next to each other. We could further condense those and just write CH2 once. and then put a subscript 2, telling us that there's 2 of those same identical groups right next to each other. Or in this case, we've got a CH3 and another CH3, both attached to the same carbon. So we could condense those further and just write CH3 with a subscript 2, then CH, CH2, CH3. So this is just a method of further condensing our structure so that we have to write even less. Okay? These are different ways to represent the same molecule. Now, sometimes you can include a bond and not show the others if you want to be specific. So in this example here, if you wanted to specify that this CH3 group right here is branching off the side, you could show that by leaving that bond drawn. Totally acceptable. You don't have to, but you could if you want to. It's up to you. Depends on the circumstance. And this CH right here, because he's only connected to one hydrogen, he just condenses as the CH group. All right, let's do some practice here. Convert each expanded structure into a condensed structure. So this is a little overwhelming to look at. And so let's try and condense it so it's easier to manage. So we want to condense this group right here. That's going to be a CH3. This is going to be a CH3. So we've got CH3 and CH3, and they're both connected to the same CH. So I'm going to connect these both to a CH. And then the next thing we've got here is a CH2. And then it looks like we've got a CH, and he's connected to a CH3 and another CH3. Okay. Now, the next one, probably a little easier. This right here is a CH3. The next carbon is connected to 2 hydrogens, so that's a CH2. That's a CH2. And this is just an oxygen. And so we're just going to write O, and we're going to leave out the lone pairs. And then we've got another CH2. And then we've got a Cl. Yeah. So these are the condensed structures for these 2 expanded structures. And it's possible to further condense these. And so notice we've got CH3 groups connected to the same carbon. So you could condense those here using parentheses around the CH3, and then the subscript 2 tells us that there's 2 of the same CH3. And we could do it again on the other side. You have a CH3 and a CH3. So you slap some parentheses around the CH3, give it a subscript 2 to tell you that there's 2 of those same group attached to the same carbon. So this is further condensed. And same thing here. We've got these 2 CH2 groups right next to each other. So we can write that in parentheses with a subscript 2. That way we don't have to write it out twice. We just write it once and then specify that there's 2 of them in a row. So this is the further condensed method. Now, before we can move on, let's talk about expanded structures in 3 dimensions. Now, recall any carbon that has 4 single bonds has a tetrahedral shape, which looks something like that. To draw a tetrahedral shape in 3 dimensions, we use 2 bonds that are just plain lines, and those are in the plane. Those are flat. We use a wedge, this big wedged bond here, to show something that's coming towards us, and we'll use the dashed line to emphasize something that's coming away from us. And so this wedge is coming towards you, the dash is moving away from you, and this is representing this molecule in 3 dimensions. And so here's a ball and stick model trying to emphasize that 3D shape here. And so this ball is coming towards you. This would be the wedge. And this one's going away from you, and so that's the dash. Okay. And all of the bond angles are 109 degrees. So it's a 3-dimensional molecule. So wedges and dashes. So keep in mind, when we draw these expanded structures, it looks like it's a 90-degree angle, but that's incorrect. These are actually 109 degrees, and this molecule is 3-dimensional. So let's take a look at C4H10. Here it is with an expanded structure. But if we wanted to draw it with correct bond angles, instead of everything looking like 90 degrees, we would draw it this way. And this shows us the proper 3D orientation where everything has 109-degree angle. Now, notice the bonds between the carbons are kinked. They have to be kinked because that bond angle is 109 degrees, right? So they make little zigzags if you look at them with proper angles. Now, I'm not going to ask you to draw these in 3D. This is just to explain where the kinks come from. Now, skeletal structures or skeleton structures are showing only the carbon-carbon bonds, aka the carbon skeleton. Now, when we draw a skeleton structure, you assume that there's a carbon atom at the junction of any 2 lines or at the end of any line. You assume that there are enough hydrogens around each carbon to give it 4 bonds, and you draw in all heteroatoms and the hydrogens attached to heteroatoms. So let's take a look at an example. Here's our C4H10 in expanded 3D. Now, if we were to condense this structure, we would have CH3 connected to CH2, connected to CH2 to CH3. Now, notice the carbon-carbon bonds here. That's our carbon skeleton. And so if we took that carbon skeleton, that would be the skeletal structure. We're only drawing those bonds between the carbons. And we assume that there's a carbon everywhere 2 bonds meet and everywhere a bond terminates. So there's a carbon here, a carbon here, a carbon here, and a carbon here. And we assume that there are enough hydrogens around each carbon to give it 4 bonds. So this carbon already has 1 bond, so that means that it must be attached to 3 hydrogens. This carbon here has 2 bonds, which means he's got 2 more hydrogens to give it 4 bonds. This carbon has 2 bonds already, which means he needs 2 hydrogens to give it its 4 bonds. And this carbon on the end needs 3 more hydrogens. And so by filling the hydrogens and the carbons in, we've gone back to our expanded structure. And so skeleton simplifies this and shows only the bonds between the carbons. This is the fastest way to draw molecules, and it's the simplest representation. So let's do some practice with this. Given this skeleton, can we draw in all the carbon and hydrogen atoms? So basically, let's go back to expanded from this. Well, anywhere a bond ends must be a carbon. So that's got to be a carbon. Anywhere 2 or more bonds meet is a carbon. So there's got to be a carbon there, carbon there, carbon there, Carbon there, and carbon there. 1, 2, 3, 4, 5, 6. So our formula is C6. Now, carbon always needs 4 bonds. So let's fill in the missing bonds. This carbon here has 1 bond shown, which means he needs 3 more. Those have to be hydrogens. This carbon has 1 bond shown, which means the other 3 bonds have to be hydrogens. This carbon here in the middle has 3 bonds already, so he only needs 1 more. This carbon has 2 bonds already, so he needs 2 more. This carbon has 2 bonds shown, so he needs 2 more hydrogens. And this carbon on the end has 1 bond shown, so he needs 3 hydrogens. So if we add up the total hydrogens, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That would be the molecular formula, and this would be the expanded structure. And it looks like we did it correct. Let's do some more practice. Given the following expanded structural formula, provide the molecular formula, the condensed structure, and the skeletal structure. So what's the molecular formula for this? Well, let's add up the carbons. So I see 1, 2, 3, 4, 5. So C5. How many hydrogens do we have? I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C5H12. Whoops. 12. Now, how do we draw this as a condensed structure? So to condense this, we need to look at these clusters of carbons and hydrogens. And so looking at this here, looks like we've got a CH3 connected to a CH2, connected to a CH2, connected to another CH2, and then a CH3. And we could further condense that as CH3. And then if we only want to write CH2 once, we just got to specify that there's 3 of them. And then we got the CH3 on the end. So that would be the further condensed structure. And how about a skeletal structure? Well, skeleton's probably the easiest. We have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5. That would be our skeletal structure. And remember, there's a carbon everywhere a bond ends, and everywhere 2 bonds meet. So 1, 2, 3, 4, 5 carbons. And just make sure that there's kinks to represent those angles of 109 degrees. And looks like we did it correct. Do some more practice. Draw the expanded, condensed, and skeletal structures of propane, C3H8. So first, let's do the expanded. Well, there's 3 carbons. Every carbon needs 4 bonds. So 1, 2, 3, 1, 2, 1, 2, 3. So that's the right number of bonds. And then we got to fill in 8 hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8. There's our 8 hydrogens. Now let's do our condensed. Well, if we wanted to condense this, looks like it's going to be a CH3 connected to a CH2 connected to a CH3. And then the skeleton, we're only drawing the bonds between the carbons, which would just be 2 bonds between carbons. So 1 carbon, 2 carbons, 3 carbons. All right. So once again, there are many ways to represent a given molecule. Today, we looked at molecular formula, expanded, condensed, and skeletal. And we also looked at ball and stick, but that's more for computer graphic generated. I'm never going to ask you to draw ball and stick models, but you will be looking at them in the book and in the PowerPoints. And in the next video, we'll learn how to name these molecules. Thanks for watching. I'll see you in the next video.